Okay, in this last part, we will discuss on how we can solve the DC analysis of a diode circuit using equivalent model. So, what is the equivalent model? Equivalent model is we want to replace a diode using passive component or combination of passive component. So we want to replace the diode with a passive component or combination of passive component. And when we replace it, we make the DC analysis become more simpler. Okay. So by replacing the diode, we need to ensure that the structure of the model will give similar IV characteristic. Okay. So the IV characteristic of the model should be identical or similar to the or close enough to the actual diode's IV characteristic. So this is the IV characteristic of diode. Okay, so for the equivalent model of diode, we have three models. So first is ideal model. So what is ideal model? So ideal model, the word ideal actually come from the ideal rectifier. So we have the rectifier, ideal rectifier. So rectifier means that allow only one direction. So only one direction. So if you have the positive and negative direction, so the ideal model, ideal rectifier is, let's say the positive direction is on and negative is off. So this is a very simple, a binary operation of rectifier. So positive voltage, the device is on or the current is there. At the negative voltage, the device is off, current is 0. So this is ideal model. So this is the explanation is shown in the circuit. So in the fault bias, since the diode is on, so the diode can be replaced by a short circuit. Okay. So on actually replacing by the short circuit. So this is a switch. You can relate it with a switch. So when the switch is on, means that there is a connection, and this is short circuit. Okay, the off state is replaced by the open circuit. Open circuit. Okay. So the diode, when the diode is fault bias, the diode can be replaced by the short circuit, one line. If there is in the reverse bias, the diode can be replaced by the open circuit. Okay, open circuit means there is no connection. So how the current voltage characteristic will looks like? Okay, so we know that if the voltage is negative, the current is 0 because of open circuit. When the voltage is positive, at the moment voltage become positive, it is short circuit. In the short circuit, in ideal circuit, the connection don't have any resistance. So resistance is 0. When resistance is 0, we have a one spike of current. So the current is in the vertical direction because the resistance is 0. Short circuit. Okay, reverse bias resistance is infinity, open circuit. So this is ideal model. Okay, ideal model is a simple switch on off. Okay, so in ideal model we neglected several parameters. One is the barrier potential. So we assume that barrier potential is 0 volt. But in actual diode, the silicon diode have barrier potential or knee voltage of 0.7 volt. And then we also neglect dynamic AC or AC resistance. AC resistance. This is in the previous part we discussed on the average AC resistance. So this is a AC resistance. So AC resistance at the on state actually should have certain value around 10 ohm, something like that. But now we assume that the dynamic resistance is equal to 0 ohm because of short circuit. And then the reverse current, we assume that reverse current is 0 ampere, means that we assume that the reverse resistance is equal to infinity. So this model is used when the exact value of the voltage of current is not concerned. So this is just a rough calculation, rough analysis. You can use this model. For example, troubleshooting the circuit, trying to figure out the operation of the circuit. Okay, let's say we solve the previous question using the ideal model. Okay, the circuit is same. We have the 5 volt connected with 2.5 kilo ohm and connected in series with diode. This is a silicon diode. Okay. First, when you have this circuit, when you using the ideal model, not ideal model, when you solving using the model, you need to identify whether this diode is fault bias or reverse bias, because you want to make a decision whether you want to replace the diode with a short circuit or open circuit. Okay, let's see here. This is positive voltage. Positive voltage is connected to the positive terminal, anode. And then negative is connected to the ground. So the anode have the higher voltage than the cathode. So means this is a forward bias. So the diode operate at fault bias. So when that is is in a fault bias, the diode can be replaced with a short circuit. So you can redraw the circuit. Next, you can redraw the circuit. Okay, so we have the diode here, replaced with the just a line. So this is a 5 volt, this is 2.5 kilo ohm, and then this is line. This should be a diode here, but this is only line here. So we have this one is ID. Okay. Now you can get the answer for VD. What is the answer for VD? Because the diode don't have any resistance is 0, so there will be no voltage drop. So VD is equal to 0 volt. Okay. So next you can calculate the ID by using the KVL. So this is same, minus 5 plus ID 2.5K, and then next there is nothing, there is no drop until the ground, so this is equal to 0. So ID is equal to 5 over 255K is equal to 2 milliampere. So this is ID. So next VR is equal to 2 milli times 2.5K is equal to 5 volt. Okay, very simple. Okay, next is practical model. So practical model is when you consider the barrier potential or the knee voltage. Okay, So in the ideal model, the sudden increase of the current occur at the 0 point. So this is ideal model. So at the moment voltage become positive, there is a sudden increase of the current. But now in the practical model, the sudden increase should occur slightly above 0. So or located at the near voltage of or the barrier potential, which is 0.7. So the sudden increase should occur at voltage equal to 0.7 volt in case of the silicon. So this is for the silicon. For germanium, this is 0.3 volt. So what in the circuit, so the diode can be replaced by the DC source or battery. So the diode in the forward bias, the diode can be replaced by a battery, and then the value of the battery is depend on the barrier potential. For example, is silicon example, in the silicon based PN junction, the DC source will have the voltage of 0.7 volt. Okay, for the reverse bias, this is similar to the ideal model where we can replace the diode with an open circuit, which is I is equal to 0 and resistance is infinity. Okay, so but the main difference between practical model and ideal model is just this 0.7 volt. So in order in order to have or in order to produce this IV characteristic, we need to use a DC source, 0.7 volt. Okay, in a practical model, the barrier potential is included, but the RD, this is the AC resistance at the on state, and RR are neglected. RR is reverse resistance, are neglected. In this case, the RD is assumed to equal to 0 and RR is assumed to have infinite value. Okay, when a forward bias equivalent to closed switch in series with a barrier potential, when the reverse bias equivalent to open switch, ideal model, same ideal model. So next we solve the practical this problem using the practical model. Okay, the first step is identify the diode is forward bias or reverse bias. So this is the same question. So we know this is a forward bias. So when this is forward bias, the diode need to be replaced with battery and a closed switch. So and then the value of the battery depend on the material of the diode. So usually if the information is not given, so assume the diode is made from the silicon. So this is 0.7 volt. So once we identify this forward bias and the model, we can redraw the circuit. So you can redraw the circuit. This is 5 volt, 2.5 kilo ohm, and this is 0.7 volt. So this is ID. Okay. Now when you use the practical model, the VD is equal to 0.7. Okay. In order to get the ID, you need to use the KVL. The KVL is -5 plus ID 2.5K and then plus 0.7 equal to 0. So the ID is equal to 5 minus 0.7 over 2.5k. So the answer for this calculation is, for the practical, is 1.72. 1.72 milliampere. And then for the VR again, just remember the VR is voltage drop at the 2.5 kilo ohm. VR is 1.72 milli times 2.5k. So this is equal to 4.3 volt. So this is the answer. Okay, and the last model is, we call it complete model. Okay, complete model actually consider almost all the properties of the diode. Okay, in a forward, let's say in the forward bias, the point where the current start to have a sudden increase, this is represented by using a DC source, 0.7 volt. And then when the current is on, the current will not, at the on state, the resistance is not assumed to have a zero resistance, but instead we put a resistor here. So this is a small RD, actually a average AC resistance at the on state. Okay, so here instead of having a vertical line, we have a we have this line with a slope. Okay, this is a forward bias. In reverse bias, we add one resistor in parallel with the open circuit. Okay, in parallel with open circuit, and the resistor is equal to small rr. So this is a reverse resistance. So by using this model, the current will not be zero. There will be a very small current flow. For example, so this is not correct. The direction is not correct. For example, this one is the current here. The current here is very small because of the RR is very high. In our previous example, the value of RR is around 10 power of 14 ohm. So you can imagine the number of the value of the current should be around 10 power of minus 15 or minus 14. So it's very, very small. So this is complete model. So complete model, VF, the knee voltage, RD, the on state AC resistance or dynamic resistance, RR is reverse resistance are included. So when forward bias, the diode act as a closed switch in series with VF and RD. When reverse bias, the diode act as an open circuit in parallel with RR. So next we solve using the complete model. Using the complete model, first again, you need to identify whether the diode is forward bias or reverse bias. So this is a forward bias. So you need to replace the diode. Replace the diode with a DC source in series with resistance. So if the diode is silicon, so this is 0.7 volt, and then the resistance here is equal to the average AC resistance. So let's say we we assume the average AC resistance is 13 ohm. Okay, this is quite close to what we have calculated in our previous video. Okay, so next you need to redraw the circuit. in order to have a clear view on the circuit. This is 5 volt, 2.5 kilo ohm, 0.7 volt. This is 13 ohm, and the VD is from here to here. And then we have ID. Okay, now you cannot get VD directly because you need to know the voltage drop at the 13 ohm. Okay, let's start with the KVL. So the KVL is minus 5, and then next is plus ID 2.5K, and then plus 0.7 plus ID 13 equal to 0, and then you can calculate the ID is 5 minus 0.7 over 2.5K plus 13. So this is equal to 1.71 milliampere. So VD is equal to 0.7 plus 1.71 milli and 13. So this is, you get the 0.72 volt. So VR is 1.71 milli times 2.5 kilo. So this is equal to 4.275 volt. Okay. Now we have already solved the same circuit using several approach. The first approach is graphical, and then next is using the model. And using the model, we have three options: whether use the ideal model, or use the practical model, or use the complete model. Okay, so let's compare the result of the analysis. So I just write down again the graphical method. The ID is 1.7 milliampere, and then the VD is 0.75 volt. VR is 4.25 volt. So for the ideal model, the current is 2 milliampere. The VD is 0 volt because there is no voltage drop because it's short circuit. So, and then this one is VR is 5 volt. So practical model is 1.72 milliampere. This is 0.7 volt, and this is 4.3 volt. And complete model is 1.71 milliampere. This is 0.72 volt, 4.275 volt. Okay. Among these approaches, actually the graphical method is the most accurate solution, provided that you read the intersecting point correctly. Okay. But the next approach that is close to the actual solution is a complete model. Okay. And then the next option is, the third best is practical model, and the last one is ideal model. But usually we use the practical model. So we ignore the small RD. Okay. So we will make sure that you comfortable doing the DC analysis using the practical model. Okay. this is the last slide that summary the model. This is the model. So what is the model? What is the point of having the model of the diode? So actually we want to imitate, or we want to replace a diode with a very simple circuit using a passive component such as DC source or the switch. So the IV characteristic of diode looks like this. Here, let's say this is 0.7. Actually, we can if the first is ideal model. Ideal model, the diode can be replaced by the open circuit in reverse bias. In forward bias, we can replace with the short circuit. And then the IV characteristic will be something like this. So at the current here is 0, negative voltage and negative voltage current is 0, but here we have the sudden increase of current at VD is equal to 0. So this is ideal. So next is practical. Practical is we consider this 0.7, the knee voltage. So the diode at the reverse bias is replaced by the open circuit, which means there is no connection, and in the forward bias is replaced by the battery with a short circuit. So the battery value is 0.7 volt. So here the IV will look like this. Okay, the current is 0 at negative voltage, and then above, after we arrive at 0.7, there will be a increase of current. So this is a practical model. And then the last one is complete model. Okay, the complete model. The complete model, we have the diode, and then at the reverse bias, there is open circuit, but in parallel we have a very large resistance, reverse resistance. Okay, and the forward bias, we have a 0.7 volt with a on state resistance. So here the IV at the forward bias, at the reverse bias, we have RR, because we have the RR, so the current is not 0, so we have the very small current here. We have a very small current here. Okay, and the forward bias, so we have the current start to flow at 0.7, and then there will be some slope here. Okay, and this slope is 1 over small RT. Okay, if you compare the IV for each ideal model, you can see that the complete model have the quite similar IV with the actual diode. This is the actual diode. So that's why the model is called complete model. But anyway, we will largely use the practical model for our analysis.